In this example, we have an equation where y is implicitly defined to be a function of x, but we want the second derivative. And so I'm going to start this out by finding the first derivative, because you have to have that first. So use implicit differentiation, which is take the derivative of both sides with respect to x. And I know on the left-hand side that means take the derivative of each term with respect to x. And on the right-hand side I have derivative of 16. And then I go through and take these derivatives. Well, derivative of x to the fourth is 4x cubed. And a derivative of y to the fourth with respect to x, you have to use the chain rule, the Leibniz version of the chain rule. And what that says is take the derivative of y to the fourth with respect to the variable you see, which is y. So here it is, 4y cubed, then multiply by dy dx. So we could formally write out those steps, but that's actually the quick way of applying the Leibniz form of the chain rule. Is if you're asked to take the derivative of some function with respect, and the variables don't match up, you take the derivative with respect to the variable that you see, and then you tack on dy dx, or dy d, whatever the variable is that you're asked. In this case, it's x. So write it out as you are getting used to doing that. But once you get used to it, you see that you take the derivative normally, but then you always tack on dy dx. Well, and then on this side you get 0. So dy dx is pretty easy to solve for. I end up with bringing the 4x cubed over and then dividing by the 4y cubed. I get that dy dx, canceling out those 4's, is equal to minus x cubed over y cubed. Now to take the second derivative, I don't have to use the original equation. I use my derivative, because I know that the second derivative, we only need 2 lines, but anyway, the second derivative is the derivative of the derivative. And so what I'm going to do is take the derivative of both sides of this, because that's how I would get the second derivative on this thing. So I'm going to have the derivative on this side. That's going to give me my second derivative, equals the derivative on this side. So I get the second derivative. I'll just do it down here. So I'm going to have the second derivative. And so I don't have to work on both sides anymore, because I know this is the second. So I'm just going to work on this right-hand side and figure out what this reduces to, and that will be my second derivative. So what I have here is it's going to require a quotient rule. I'm going to pull that minus out. It's going to be the derivative of the x cubed times y cubed minus the derivative of the y cubed times x cubed, and then that's all going to be divided by the y cubed squared. So when we go through and take those two derivatives, this is going to be 3x squared times y cubed minus, here we go again where the variables don't match up, so I'll have to take the derivative with respect to y cubed. I'll have to take derivative first with respect to the variable I see, which is 3y squared, and then tack on dy dx from the chain rule. And then there's this x cubed that was there from the quotient rule. And all of that is divided by y to the sixth. So this dy dx shows up again. But fortunately, we have a formula for dy dx that we just came up with. And so I'm going to replace dy dx in this second derivative formula by what I know dy dx is equal to. So this is going to be minus 3x squared y cubed minus 3y squared. Dy dx is minus x cubed over y cubed. Not making a 3, but that's a 3. And then that is all divided by y to the sixth. Let me make sure I got it right. Yes, x cubed over y cubed. And so now the dy dx is gone, so it's just a matter of simplifying this as much as I can so that I'll have my formula for my second derivative. Well, I've got my minus 3x squared y cubed. This is all going to become positive because of that negative that popped up. I'm going to be able to cancel out some of the y's here and be left with 3 x to the sixth over y. That's what will be left in that term when you cancel out 2 of the y's. And that's all still over y to the sixth. Well, I don't want that y in there like that. So what I'll need to do is multiply both sides by y over, top and bottom by y over y to clear out that fraction. And so when I do that, I'm going to have a minus 3x squared. This will be a y to the fourth now, plus 3x to the sixth, because that y will be gone. That's all divided by y to the sixth, y to the seventh now. And I can factor a 3x squared out of the top, so I'm going to have minus 3x squared times, there'll still be a y to the fourth, and this will just be x to the fourth over y to the seventh. And maybe this looks familiar, maybe you saw it somewhere before. Well, let me scroll all the way back up. I get to go back to this as well. X to the fourth plus y to the fourth is actually 16. So I need to put that in because that makes it even simpler. So this is going to be minus 3x squared over y to the seventh. That's 3x squared times 16 y to the seventh. So my final result here is that the second derivative is equal to negative 48x squared over y to the seventh. So it's a long process. You have to get your first derivative first, and then you take your second derivative. What's going to happen every time, as long as your first derivative has a y in it, and it should if you're using implicit differentiation, otherwise you don't need implicit differentiation. But your second derivative is going to have a dy dx showing up, so you just replace it by what you calculated dy dx to be. And then sometimes this happens as well. Your original equation might show up that you can use to simplify even further. But that's the process of finding a second derivative of implicit functions.